SpaceX's Starship is massive. It's 9 meters wide, and just the upper stage is over 50 meters tall and over 100 metric tons of dry mass. And as incredible as its enormity is, it does make for an unwieldy and frankly ridiculous lunar lander. In 2021, NASA chose Starship to be one of the human landing systems, or HLS, for their Artemis program. That's right, this behemoth is over 7 times taller, probably about 100 times heavier when landed on the moon, with over 100 times more internal volume than the Apollo lunar lander. With this enormous lander comes huge challenges. I mean, just look at how tall this thing is. Doesn't that make it super prone to tipping over? It's also going to use cryogenic Methalox propellant that will boil off and is more difficult to ignite than the conventional hypergolic propellants that are often used on long duration missions. And what about its biggest problem? The fact that it's going to require a dozen or more launches to fill it up in low Earth orbit in order to get it out to the moon. I'm Tim Dodd, the Everyday Astronaut, and today we're going to try and figure out if Starship HLS really is a viable option for NASA and SpaceX to get humans back onto the surface of the moon for the Artemis program. So we'll dive deep into each one of these problems and we'll go over their solutions and see if we can figure out how, or maybe I guess more importantly, why SpaceX is trying to land a skyscraper on the moon. Okay, let's get started. Now, before we get into all this, I just wanted to point out here that although this video is a super deep dive on a lot of aspects and the math and science of Starship HLS, there's still a ton of information that we simply don't know anything about. We don't have any real information on the landing thrusters or really much information on the inside, like the toilets or the crew cabins or the elevator or micrometeor and radiation shielding or solar panels and all sorts of things we just don't have any details about. And that's okay. This video is more about the overall feasibility of landing a 50-meter tall Methalox-powered skyscraper on the moon that requires a dozen or more refilling tankers to get it filled up to do any moon landing mission. And one more thing before we get into all this, if you like any of the music you hear in this video, you can find it on my new full-length album called Direct to Orbit, which is available anywhere you stream music. Enjoy. And don't forget to check out our new Translunar Coast collection. That features our sun-kissed isocyanate shirt that's a nod to the compound that gives SLS its iconic orange color, our slow roll towing shirt, Translunar Coast shirt, Artemis X Core hats, and more at everydayastronaut.com/shop. Okay, enough shameless self-promo, now onto this mega long deep dive. And because this video is so long, here's the timestamps. The timestamps are also in the description, and if you're watching this on YouTube, the play bar is broken up by these sections too. So all that said, let's dive into Starship HLS, or the Human Landing System. So the current plan is to launch the HLS Starship into LEO, which replaces the standard Starship upper stage. So it'll get itself into orbit from the booster, meaning it'll arrive into orbit basically empty. Now it's going to lack the signature flaps and heat shield, but it will have a massive pressurized crew compartment with 2 massive airlocks that sit near the top of the vehicle that will require an elevator to get down to the surface. It'll also require enormous self-leveling landing legs to hopefully help it stay upright on the unprepared and uneven lunar terrain. And don't forget, it'll also feature landing thrusters that are unique to the HLS variant. They're pressure fed and they sit near the top of the vehicle, so they don't disrupt the lunar surface too much when they're trying to land a vehicle that weighs hundreds of tons on that loose lunar regolith. They're only going to be used for the very last portion of the landing profile, and they'll also use them to take back off from the moon until they're at an altitude safe enough to light the Raptor engines. So that's Starship HLS. Next, let's go over a few important things that you're going to hear often in this video, starting with specific impulse, or ISP, which is just a measure of how efficient a rocket engine is, measured in seconds. But it's actually just the exhaust gas velocity, or how fast the exhaust is shooting out of the rocket engine. So the higher the specific impulse, the better, which really just means the faster the gas is shooting out, the more efficient it is, the better it is. Another term you're going to hear a lot in this video is delta V, and it's probably one of the most important concepts in this video. Delta V means change in velocity, or simply how much a vehicle can accelerate. But it's probably just easier to think of it like the range of a car. If you ignore drag and rolling resistance, the range of a car is pretty much just a factor of how efficient its engine is and how big its gas tank is. We'll measure delta V in meters per second in this video. It'd be foot per second in imperial, but it could even be kilometers an hour or miles an hour. It's all just a measure of how much a vehicle speeds up or slows down by. Let me show you how we calculate delta V by using HLS as an example. So to solve for delta V, we need to know our wet mass, or our starting mass, which is how heavy the rocket is when it's fully fueled, or at least how heavy it is at the start of the burn we're trying to calculate. And then we need to know our dry mass, or our final mass, which is how heavy the rocket is when it's empty, or at the end of the burn that we're calculating. But this does need to include the mass of any payload, or any stage on top of it, or any propellant that's not being utilized in that burn. Then we need to know the performance of the engine based on its exhaust gas velocity in meters per second, which we can convert from its specific impulse number by just multiplying that by 9.8. Then we take the exhaust gas velocity times the natural log of the wet mass divided by the dry mass, and we get the delta V of the rocket. Now remember, delta V isn't just a fixed number for each rocket or each system. It depends on the payload mass. Since the payload mass affects that wet mass and dry mass, changing the payload does change the delta V. Same with if we have different reserves of fuel, that's going to change the delta V for that burn. Now it's important to note that delta V isn't linear with propellant, meaning if you double the propellant of a spacecraft, you don't double the delta V because you increased its mass too. So if you double the propellant, your rocket now has more mass to push around at the beginning of the burn, and therefore it can't do as much work proportionally as it would at the end of the burn when it's emptier. This is called the tyranny of the rocket equation, and it's why it's so difficult to scale the performance of a rocket system up. And it's also why rockets do staging, so you get to start over with a fresh new rocket with every single stage. Okay, now that you know what delta V is, let's do a quick overview of the mission plan. Now we'll be going over these numbers in a lot more detail later on, so don't get too hung up on it right now. But first, I just wanted to give you a sense of the mission plan. So I have this little chart map thing that shows different mission milestones on the right and their delta V requirements on the left. But I did want to point out here that these maps and most of this video talks about meeting Orion in near rectilinear halo orbit, or NRHO, which is a highly elliptical orbit that has been chosen for the Artemis program due to the limitations of SLS and Orion. But this rendezvous point could change later on in the Artemis program. However, it should be noted that the total amount of delta V to get from low Earth orbit to the surface of the moon doesn't really change that much, whether you target that near rectilinear halo orbit or a polar low lunar orbit first before you land on the moon. Now, NRHO does require a couple hundred meters per second of delta V extra, but the bigger deal is that it's harder for the landers to go from the surface of the moon all the way back up to NRHO over and over for subsequent missions. So as far as how much work the lander has to do, it's harder to get to and from NRHO than it is low lunar orbit. So throughout this video, we'll do our calculations based on NRHO, since it's the worst case scenario that the first few missions likely will have to target due to where the lander will need to meet up with Orion. But at the end, we'll also calculate the best case scenarios where we don't target NRHO, we just target low lunar orbit, and we see what effect that has on the missions. The point being, if they can do NRHO to the surface and back, they can also even easierly, they can even easier do low lunar orbit to the surface and back. So just keep that in mind, that throughout this video, that this is something that could change for the better as far as it goes for the landers. And I should also clarify something real quick here. We're going to be using the term tankers and depots. Tankers we'll consider to be starships launched into low Earth orbit that dock with a depot. So there might be a dozen or more tanker launches to fill up a depot. And depots are the vehicles that actually stay in space. They don't have flaps or heat shields, they're optimized for space. And once they have the amount of fuel necessary for any given mission, in this case HLS, the depot will dock up to it and then transfer all of that propellant over. But we also will be talking about using a cislunar depot of some kind that refills HLS when it's all the way out at the moon to be able to do another mission down to the surface and back. Now this could be the same depot that stays in low Earth orbit, or it could be a bespoke one that's optimized specifically for these cislunar trips to be as efficient as possible. We'll maybe assume that they actually have a separate cislunar depot. Okay, anyway, here's our mission overview. In order for HLS to get out to the moon from low Earth orbit, it needs to get filled up once it's in low Earth orbit. So SpaceX will have to get, 1,200 or 1,500 tons or however much, we'll calculate that a little bit later, into low Earth orbit to fill it up. And what that means is with Starship's 100-ton payload capacity, that would be 12 or 15 or more launches of Starship tankers to get enough propellant into a depot that has minimum boil-off, that then has to dock with HLS and transfer all that propellant over so HLS has enough energy to do its own translunar injection. And now, depending on the final configuration and mass of the vehicle, there's a chance it'll need one more topping off on the way to the moon, either in medium Earth orbit or perhaps once out at NRHO in orbit around the moon from some kind of refueling depot or a tug. Now we'll get more into those exact numbers here in a minute, but after the TLI, HLS will get into near rectilinear halo orbit to meet up with Orion. They'll dock in NRHO, and then the crew will transfer over into HLS from Orion. Then it will need to lower its orbit from NRHO down to low lunar orbit and then land on the moon. Then it has to have enough propellant left over to be able to do the ascent back from the moon up into lunar orbit, then into NRHO so it can meet back up with Orion, so the crew can transfer back into Orion so it can get back to Earth safely. So this means in order to do this mission again, they'll have to get enough propellant back into HLS while it's all the way out there at the moon. It's likely going to need something like over 500 or 600 tons, which is a number we'll play around with here in just a minute. This means you have to get enough propellant into a translunar tanker depot thing of some kind that would require another dozen or more, or 15 or 18 launches to fill that up so it can go all the way out to the moon, transfer that 500 or 600 or more tons of propellant into HLS, and then it needs to have enough propellant remaining to come back down to Earth, perhaps hopefully using some kind of, light aero capture or multi-orbit reentry. At this point, you might be asking yourself, why on earth does it require all these refueling launches when the Apollo program not only launched the lunar lander, but also the command and service module in a single launch? What happened? Well, like we mentioned at the beginning, HLS is massive. They're trying to land something like 500 tons on the surface of the moon. So nearly 100 times the mass of the Apollo lunar lander with 100 times the internal volume. It's just absolutely massive. And now because of this, SpaceX is trying to cheat the rocket equation here. Because when the Apollo LEM landed on the moon, it was only about 7 or 8 tons depending on the mission. So 7 or 8 tons out of a rocket that weighed almost 3,000 tons. So yeah, that's only about 0.25% of the liftoff mass is actually what landed on the moon. And that was despite using super efficient architecture like separate ascent and descent staging, expending all the hardware, including expending the Saturn V rocket and lunar rendezvous. Despite all this, they could only get about 0.25% of liftoff mass that actually lifted off from Earth onto the surface of the moon. So because Starship HLS is something like 500 tons when it lands on the moon, they're trying to get more like about 8% the takeoff mass of Starship to the moon. So if you were to use the same convention as the Saturn V to land a vehicle the size and mass of HLS on the moon, the rocket lifting off from Earth would have to be something more like 200,000 tons, or about 67 times more massive, which, although that's obviously ridiculous, that'd only be about 4 times taller and wider than the Saturn V thanks to volume scaling by the cube of linear dimensions. But 200,000 metric tons liftoff mass. And of course, don't forget, it would all be expended, which of course, Starship is hoping to be fully reusable. So yeah, that's why these refueling trips are necessary. And by reusing hardware, in theory, nothing should be thrown away except for propellant. So it's not like each launch is billions of dollars worth of hardware. It should someday just be a few $1 million worth of propellant. Hopefully. At least that's the big eventual bet here. Okay, now let's lay down some baselines. Now these numbers are not going to be perfect, and that's okay. This video is more about teaching you how to calculate this stuff and what variables make what impact. I'm certainly going to be off by quite a bit, but luckily there have been a few numbers that have been published, specifically some of the numbers from this post. We don't know the true dry mass of HLS. It's probably somewhere around 120 tons or so. Now this is just a rough estimate given the amount of hardware necessary for life support, the cabin, landing legs, airlocks, those landing thrusters, boil-off mitigation, the solar panels, the sleep cabins, etc., etc. Who really knows? But this is all good enough for a rough estimate. And we'll assume it has that same 1,600 tons of propellant mass as the standard version 3 Starship for our baselines. Now let's talk about the rocket engines, starting with the vacuum Raptor engines, which get about 380 seconds of specific impulse, and it weighs about 2 tons per engine. A Starship HLS variant will likely only use 3 in order to minimize dry mass, although they might use 6. It just depends on the trade if that's worth it delta V wise. Then there's also the sea-level Raptor engines, which get about 350 seconds of specific impulse, and they weigh roughly 1 ton per engine. They will still use 3 of these, even though this vehicle will be in space the whole time, in order to maintain attitude during these burns, as we see them do on ascent, because the sea-level Raptors are the only ones that can actually gimbal and steer. Now, if we throttle those sea-level engines down to 66% throttle, we can average their ISP to be 370 with the vacuum engines. We'll use that number for our rough estimates to calculate delta V. Next, we have those landing thrusters, which are pressure-fed off the ullage tanks and give roughly 320 seconds of specific impulse or so. There's a few tricks that could maybe get that number closer to 330, but we'll just use 320 for our estimates. And we really have no idea of the dry mass of each thruster, let alone that whole cluster of thrusters, nor how much all their plumbing and everything weighs, and it doesn't really matter, it's all just lumped into the dry mass anyway. I mean, same with the Raptor engines, those are also included in the original dry mass number, but I wanted to have an estimate of their mass in case we change them around at all in some of these upcoming configurations. Okay, now that we understand delta V and the rocket equation, we've seen the mission profile and the hardware, you probably already have a good sense of some of the challenges. But now, let's really dive into them. In this section, we're definitely going to be diving into a lot of numbers and get really deep into this kind of stuff. But first, let's take a look at that most obvious problem, the height. Starship is over 50 meters tall and 9 meters wide. So a height to width ratio of over 5:1. Compare that to the stout Apollo lunar lander that was actually wider than it was tall. It was 7 meters tall and 9.4 meters wide, so more like a 1 to 1.3 ratio. And I think some of us might have some recency bias here of lunar landers because of NASA's commercial lunar payload services, or CLPS, because it sure seems to be reinforcing this idea, considering that 2 of these 3 landers have tipped over and only 1 has landed successfully. Can you guess which one? So is Starship doomed to tip over? Well, for this, I think we need to keep a few things in mind, like, if they do self-leveling landing legs, that'll sure help. But we also need to know where the center of mass is. And I think for this, we should maybe break out an advanced parametric spacecraft, CAD, that has an integrated center of mass calculator for lunar gravity environments. I'm just kidding. Of course, I'm talking about Kerbal Space Program, the good stuff. So let's look into this. Okay, welcome to Kerbal Space Program, one of my all-time favorite games. Sorry for this really ugly Starship HLS vehicle. It's got the parts that matter. It's got the goods, and this is good enough to be able to demonstrate. So we've kind of got, a whole crew compartment up top with some airlocks and a bunch of mass up there to simulate, the cabins and all that kind of stuff. We've got some solar panels. We've got the landing thrusters up here, the ring of landing thrusters. We've got some RCS thrusters. We've got landing legs. We've got 6 engines, 3 vacuum and 3 sea level. We've got the kind of stuff good enough here to represent what we're looking at. So let's start off by looking at the center of mass. So you'll see the center of mass is, it's not, it's about 1/3 of the way up. But there's something there's a few things we need to take into consideration. First off, it'll be about 1/3 of the amount of propellant by the time it lands on the moon, so we can lower these numbers. But there's also going to be some kind of downcomer between the methane tank that goes down to the engine. So we can have it so this is totally full, and we'll reduce the amount of liquid oxygen there. So now that will help reduce and it might even be less than that. There's a lot of tricks they could do. They could basically, if they wanted to, do almost coaxial tanks and have it so all of the mass of the propellant sitting in the bottom of the tank near the very bottom of the vehicle. That would sure help. But yeah, the center of mass is around there. The other thing that I did is I made it so the landing legs can individually extend, so we could actually help level it once it does touch down on the moon. That might be a very active system that is preemptively, seeing the slope and calculating the slope and doing that. I'm gonna do it manually. If I can do it manually, a computer will be able to do it a lot better. So let's take this out and actually see what it looks like when it's trying to land on the moon. Welcome to low lunar orbit, and with our Starship HLS, we're just in the equatorial orbit, doesn't really matter. I'm just gonna show you kind of how you do this landing procedure and what it looks like, especially if we're landing on some slopes. So we're gonna be aiming for some slopes. So first off, let's fire up our Raptor engines, and we're gonna go ahead and slow down. So we're kind of doing our deorbit burn, and we're gonna aim for this group of nasty craters right about there to try to land in. So we've cut the engines now. That's our ballistic trajectory will get us right down into those craters. Looking for some steep slopes to try to land on. Now let's go ahead and speed up. Now, of course, they won't be targeting slopes, but I'm just gonna demonstrate like what it's like if it were to end up trying to land on very uneven surfaces, what those self-leveling landing legs would actually be capable of doing. So it looks like, whoa, here we go. This is some serious terrain here. So let's go ahead and start slowing down and try to land on, we're gonna bleed off all of our horizontal velocity first. Again, still using those Raptor engines. And we'll go ahead and try to land on some of these really steep slopes here that we see. These are kind of nasty. So there we go, horizontal velocity basically cut out. Notice that it's pointing pretty much perfectly. And at this point, Raptor engines are done. We bled off our horizontal velocity. We can now switch over to our really loud landing thrusters. And the idea is, yeah, that we don't want any horizontal side-to-side motion at all. So we're gonna be kind of studying that, making sure that I kind of nailed it. So the big thing now is I gotta be, slowing down a little bit here. And you can see, wow, we are going to be landing on quite the big slope here. This is way steeper than anything NASA and SpaceX would land on. But just for an example here, let's go ahead and get real close to the surface, and then we can start playing around with the landing legs here. So here we go. Now we can also see that we have no horizontal velocity. We are dialed in. I don't know, that was lucky on my part. But here we go. We definitely need to extend this landing leg and this landing leg to be able to help us land fairly level. We do have a little bit of, there we go. Let's see even more on this one. Okay, let's cut the engines. Look at that. Hey, that's pretty good. And even if we turn off RCS, not bad. And the computer will be able to do a lot better job of this using, radar, LiDAR, cameras, all this stuff to be able to look for slope and boulders. And despite, me being a measly human, we're pretty close to level with the landing legs. I mean, I can go a little bit higher to be able to get this thing to actually be on all fours and pointed so that the attitude indicator makes it so we're pointing straight up and down. That would be a highly successful landing in my book. So, I mean, it just goes to show with self-leveling landing legs that, yeah, you really could land on really, whoa. You could really land on some tippy surfaces here, some nasty slopes, and it'd be able to survive. Obviously, like I said, SpaceX and NASA wouldn't be landing on this steep of a slope, but it does go to show that with the right hardware, and as long as you can kind of do the, remove all your horizontal velocity, the last little landing bit is actually quite simple. And SpaceX is really good at propulsive landing. They've kind of nailed that down. But even for them, this is still a huge challenge, but it's not impossible. And assuming they do really have self-leveling landing legs, I don't know. I mean, I think it could work. But now for those of you curious, I will show you what the takeoff will look like. It'll just be the reverse. So we'll just accelerate here, get a little bit off the surface, a little ways above the surface. And then we can just kind of kill these engines here in a second and pitch over to a safe so that we're not firing the Raptor engine straight down, light up the Raptor engines, and accelerate into orbit. And there you go. We'll just do the reverse and head off into orbit. Pretty cool, right? So the reality is, I'd probably prefer a wider set of landing legs or a shorter HLS. Either would make me just kind of feel better, and sometimes that matters a lot, right? I mean, that's gotta be enough, the feelings, right? But not to mention, if it was shorter, we also wouldn't have as big of considerations for the elevator. It wouldn't have to be quite so extensive. However, let's not forget the Falcon 9, this beautiful thing that you can find at everydayastronaut.com/shop if you want your own metal Falcon 9 rocket. When they first were trying to land, everyone was going, look at those tiny landing legs compared to how tall it is. I mean, we're used to it now, but when they were first trying to land, everyone was saying these landing legs are way too small. They're never gonna be able to land that thing. And even if they do land, it's not gonna survive on a rocky ship. And yeah, they had their moments with it, but it turns out, now they land like every other day and they don't tip over. So, and we're used to it now, but at one point it was pretty wild. But still, in my opinion, anything we can do to decrease the height would be a win-win. So back to those landing thrusters near the top of the vehicle. Like I said earlier, we don't currently have pretty much any details about them, but that's okay because their purpose is the same regardless of their details. They're way up there to basically prevent creating a giant crater that Starship would have to try and land in, because firing up Raptor engines right above the surface of the moon would definitely be a bad idea. Now sure, the Apollo lunar lander didn't really leave any noticeable crater, but the lunar lander only had a little over 45 kilonewtons of thrust at full throttle, and it was of course closer to half throttle when it was touching down. A single Raptor engine at minimum throttle still produces about 1,500 kilonewtons of thrust. And don't forget, you'd want to have two of them running in order to provide roll control for a vehicle like this. That's over 65 times more thrust than the descent stage at maximum throttle. And again, the descent stage was probably closer to half throttle near touchdown, so it's probably more like 100 times more thrust. This is about the same thrust difference between the Redstone rocket, whose launch pad and flame deflector looked like this, versus the Saturn V, whose launch pad and flame deflector looked like this. So having landing thrusters near the top are there for this exact purpose. They can help in a few ways. First off, by being high up, the exhaust coming out of the thrusters spreads out over a much greater area, leading to less ground disruption. And it's diffused through several chambers in nearly 360 degrees around the vehicle, which again helps the exhaust from being localized on one small area. These two things, although they'll still undoubtedly kick up a lot of lunar regolith, should help prevent Starship from making an unlandable crater under its own feet. But what about that elevator? We need to use an elevator to get down to the surface of the moon? Is this really the best idea? A 40-meter long cable-driven elevator system with all the lunar dust and everything? This seems pretty crazy, right? Well, I suppose it's relatively simple and it would be effective, but what if it doesn't work or it stops working? Couldn't it potentially leave astronauts stranded on the moon? Yes. Well, you're not alone with that worry because NASA also expressed concerns with the lack of a backup. The solution? Well, you could fairly easily have a backup ladder integrated into the side of the vehicle, which I think would be a no-brainer because it's pretty low mass and would be fairly easy for a crew to be able to climb up in an emergency because of the moon's low gravity. There could also be auxiliary battery-powered winches or secondary ways to power the elevator or individual hoists. Again, this is much easier because of the 1/6 gravity. But this all raises perhaps one of the biggest questions I get asked about most often, which is, why don't they just land this thing on its side? Then you wouldn't even need an elevator. You could perhaps just have like a slick staircase, more like a jetliner or something. Why don't they just land this thing horizontally? Well, for that, I think we should actually go back into Kerbal Space Program. Okay, so we're back in the vehicle assembly building here. And first I wanted to show you one of the benefits of kind of doing this vertically. That's maybe a little bit counterintuitive, but it's the concept that when you have a vertical vehicle like this, your center of thrust, so where all your engines are aiming, goes through your center of mass. So as you're draining propellant from the vehicle, you are not changing that center line thrust. So the thrust is always going up more or less through the center of mass. So even if we turned off these engines, does that do that for all of them? Yes, and even these thruster engines up here, the center of thrust still goes right through the yellow center of mass ball there. Now, of course, during landing and stuff, if you had an engine go out, you would want to cancel the opposing engine so that you don't start to, induce anything. But as propellant drains, that ball's just going to change. It'll move up and down, like this. It's not going to change left, right, forward and back. It's just going to change up and down. So your center of thrust is always going through your center of mass. So now let's scrap this though, and let's try and build a quick little vehicle that lands horizontally, and I'll show you kind of some of the little underlying issues there. Okay, so I'm getting close to having this thing ready to land horizontally, and I'm already struggling with one of the biggest problems, which is getting my thrust to line up with the center of mass. So what I clearly need to do is lower a lot of these engines, these landing engines down, which will hopefully get it more in line with the center of thrust, or center of mass. That looks a lot better. There we go, about like that. So now our center of thrust is in line with our center of mass. However, don't forget, as we burn propellant, this will be shifting. So let's see how that plays out. Okay, welcome back to the moon. We are going to do the same thing we did last time, which is basically just deorbit. So I'm just gonna put us down. I'm gonna put us down a lot closer just so we can start working on the final landing part, because it doesn't really matter. Actually, it'd kind of be nice if it was a flat area. It'd help us demonstrate kind of the issue. So right now, our frame of reference here is still going through the nose of the vehicle for what is up. So when we're firing the Raptor engines, we're using that as our frame of reference. And now that we're a little closer to the ground, I'm gonna go ahead and cancel out our velocity here. And then so we're still pretty far above the surface. Then I'll switch over to going horizontal. There we go, that's good enough. So now, right now our frame of reference is like this, but if I click here, it's going to switch to this top little port here. Now that's our up frame of reference. And I'll turn off our Raptor engines, I'll turn on our landing thrusters. And in real life, what would happen is you'd have to use something called differential thrust. So basically the engines have to thrust higher and lower to maintain attitude and maintain orientation. I don't have that option in stock Kerbal with these engines, but I do have the option of using little RCS thrusters. So I have a ton of reaction thrusters to make it so I can do this control scheme. But the problem is, like I said, is that the center of mass is shifting as we're burning propellant. So if I actually turned off our thrust differential, you can get a good sense of what would happen right away. Watch this. You'll notice, oh, even though our center of mass was good, now it's off. And the front is lighter than the back. Like I said, we can cancel it out. Computers can do all that stuff, but it is a disadvantage of this control scheme. So I'm gonna keep putting her down here. That was just kind of a demonstration. But I think once we get a little bit closer here to the ground, you'll notice probably our other bigger concern. It's actually, I mean, it's doable for sure. Don't get me wrong. And potentially they might actually do something like this someday. But as you get closer to the surface, you will notice one bigger problem. And that is obviously that these engines are quite a bit closer to the surface. So you're producing the same amount of thrust as before. However, now instead of being, really high up, 40, 50 meters off the surface, you're now only a couple meters off the surface and providing that same blast. So if you're trying to prevent massive lunar regolith, dust going everywhere like crazy, creating these big craters, it would certainly be a lot harder with engines this close to its landing. So I made that look fairly easy, and obviously a computer would make it even easier. But the reality is it is actually quite a difficult control scheme. If you have a problem with an engine or something, it just has so much torque on the system because your center of thrust is not in line with your center of mass. It's shifting, and you have just these big lever arms of engines way out there on the edges. So landing horizontally has some compromises, and actually probably the biggest one that we didn't really talk about is structurally. So now, the rocket's designed to handle loads going up through it vertically. If you're landing horizontally, you just have some additional loads that you have to account for. But the reality is the biggest reason probably is just that it's actually quite hard to control, and that it then also disrupts the ground quite a bit more. But in the long term, once we have additional vehicles at the moon, going back and forth, wouldn't it maybe make sense to potentially just lay these things down anyway? And to answer that, I would say that definitely could make sense. In fact, Joe Montenegro and a team called Team Lunar came up with this incredible Starship-derived moon base idea called Rosa's Moon Base. And here they envision tipping Starship over and repurposing it as a moon base. Then you could excavate lunar regolith to cover the vehicle for both micrometeor and radiation protection. And I think this would be a fantastic concept for long-term moon bases. Like I said, we're not really going to get into things like micrometeor and radiation protection in this video because those are definitely long-term problems anyway. For shorter 2-week missions like what's initially planned, it's just not a huge concern. So to summarize, if SpaceX ends up using self-leveling landing legs, if they use those high-up diffused landing thrusters, and if they bleed off all their horizontal velocity before touching down, in theory, landing Starship HLS is physically possible, and this is actually, in some ways, a fairly straightforward approach. But like I said, I still think shorter is better, but we'll talk about shorter Starship options later when we deal with smaller landers and their numbers. But first, we have another problem that's actually quite a big one: the propellant. So for the propellant problem here, Starship uses Methalox, so liquid methane for the fuel and liquid oxygen for its oxidizer, which has two problems that make it not a great choice for a lunar lander. First off, unlike the Apollo lunar lander and lots of other landers and spacecraft who have to operate on long-duration deep space missions, Starship isn't using hypergolic propellants. Hypergolic propellants are those that spontaneously combust when the fuel and oxidizer come in contact with each other. Hypergolic propellants make ignition inside an engine or thruster extremely reliable and simple. As long as both propellants arrive in the combustion chamber at the right time, you will have ignition, period. There's no point of failure there. If you want to learn more about the ignition process and the rest of starting a rocket engine up, I've got a deep dive video on that topic. But ignition isn't really my biggest concern, because the more Starship flies and the later into the program this all occurs, there'll be hundreds or literally thousands of ignitions of Raptor engines by the time you consider that each flight has, 39 Raptor engines, maybe later 42, and all the ground testing. Raptors fire a lot. At some point, you could just end up with an engine that's been fired so often, you likely will have uncovered edge cases, or at least the vast majority of them, and weeded out problems, and you can get extremely reliable ignition. Similar to how reliable the Merlin engine has become. I mean, granted, it does kind of use a form of hypergolic pyrophoric ignition, but it's incredibly rare to see it fail to ignite for reentry or landing burns. So ignition is a problem that might just simply be solved with an absurd amount of tests and flight data where you start to weed out the edge cases. In my opinion, the bigger issue with using Methalox as a propellant is the boil-off. Now, we've kind of mentioned it here briefly, but let's dive into this a little more. Methalox is a cryogenic propellant, meaning both the fuel and oxidizer are only liquid when they're stored at extremely cold temperatures. And even though, yes, space is technically very cold, it's really just the absence of air molecules that makes it cold. This means that there is no air molecules to absorb, hold, or transfer heat to or from any objects in space. There's only radiation to transfer heat in the vacuum of space. This also means that a spacecraft that's in view of the sun is just taking in a lot of heat energy, about 1,370 watts per square meter in low Earth orbit. But if you're in Leo, you also have Earth's reflected light and radiative heat to contend with as well. This averages out to about 1,135 watts per square meter of absorbed thermal energy while orbiting the Earth. A spacecraft eventually reaches a temperature equilibrium where it's radiating as much heat as it's receiving. This includes the propellant inside the tanks that will eventually also warm up to reach part of that equilibrium. This is another reason why most deep space spacecraft use hypergolic propellants. One of the most common propellant combos are hydrazine for fuel with a boiling point of 114 degrees Celsius and dinitrogen tetroxide for the oxidizer, which has a boiling point of 21 degrees Celsius. This means they're within an operating temperature range where the propellant will remain a liquid when in space and not boil off with minimal considerations. And it's very important to keep your propellant as one state when an engine is running. If an engine ingests gas bubbles, it won't be around much longer to tell you about it. But for methane, its boiling point is minus 161 degrees Celsius, and for oxygen, it's minus 183 degrees Celsius. And like any liquid, when warmed up beyond their boiling point, it turns into a gas and it expands. And because a rocket is a giant sealed container, it means when these liquid propellants warm up and boil off, you have to vent them out so they don't raise pressure beyond the constraints of the tanks and rupture them. Because that, of course, not be good. This ultimately means each day you lose some of your propellant to boil off. It's propellant that was inside the tank and now needs to be vented off into space and is now just not part of the propellant you can use for your mission. And this amount is non-trivial. It can be as bad as 1% per day. So long duration missions, including the depot that's filled up and just waiting for Starship HLS in LEO, or Starship HLS itself on its way to the moon, or on a long duration mission on the surface of the moon, there's a substantial amount of propellant that can just simply disappear. So what's the solution here? How do we prevent Starship from losing all of its propellant to boil off? After all, doesn't this mean if we had a depot in low Earth orbit waiting for Starship and had 1,600 tons of propellant, if it lost 1% per day, wouldn't that mean in less than a week it'd already lose 100 tons and require another top off? Well, let's start off with the easiest solution: orientation. If you orient the vehicle so its engines are pointing at the sun, you greatly reduce the cross-section of Starship exposed to the sun. Doing so reduces the area receiving sunlight from about 450 square meters to only about 64 square meters. The next easiest solution is insulation. You've likely seen gold insulation on spacecraft before, and it's there as a thermal insulator. And if you do a multi-layer insulation, or MLI, like the sunshade of the James Webb Space Telescope, you can effectively cut heat flow to just 1%. And you can also put your solar panels in front of an MLI sunshade, which also helps, again, reject heat, but would capture electrical energy that we could use to power an active cooling system that could effectively keep the propellant at a liquid state continually, so completely mitigating boil off. And you can also use a secondary vacuum jacket inside the tanks, like a thermos, to also help keep the propellant from receiving the majority of heat. Combine forces with all of these and you can literally effectively solve boil off. Even doing a little a la carte of some of this and some of that, we can drastically reduce boil off to the point of it really not being an issue. But of course, each consideration requires real engineering, real mass, real hardware, real complications. So lump this into it's not physically impossible to use Methalox, but it certainly has compromises that have kept it from being the conventional option. And let's not forget that Methalox has already been proven as a viable propellant for lunar landers, because Intuitive Machines has already used Methalox for both of their Nova-C lunar landers, which despite them not landing upright, they did prove to successfully tackle the challenges of using Methalox. So why are they using Methalox? Well, first off, it's what's used in the Starship system, and this means they don't have to re-engineer engines to run on a different propellant. And keeping the propellant in family with everything else means no special considerations for unique operations, just for the hypergolics, which keeps costs down and simplifies ground handling operations and ground service equipment. Second, it's high performance. Like for like compared to hypergolic fuels, Methalox will have better specific impulse by quite a bit. Despite hypergolics being more dense, meaning they would need smaller tanks for the same mass of propellant, Methalox's higher performance still wins out. Third, hypergolics are horribly toxic and extremely reactive, and therefore they're a big deal to handle in terms of filling up a vehicle on the ground, transporting, or just even firing a rocket engine anywhere near humans. And now imagine having to transfer hundreds of tons of highly toxic and reactive propellants at the moon. No thank you. So speaking of Methalox and all this propellant, now it's time we address the biggest elephant in the room. Why oh why will it take a dozen or more refilling tankers to do one moon landing? That can't be right, can it? Does Starship really require a dozen or more tankers to fill up its Starship HLS for a single moon landing mission? Well, to really answer that question, I'm once again going to go off script, and I'm going to go into spreadsheet land. Now hold on, don't you go anywhere. I think this is the best way to actually understand this stuff, and we can learn a lot just from playing around with the variables. This is the ultimate lesson in compromises and in cascading effects, because if you change any one little thing, it changes absolutely everything. So the knock-on effects are enormous. So check this out. Okay, I think a good place to start here is to actually look at the full stack of Starship and Super Heavy Booster, because then we can kind of see the knock-on effects that that has with any change we make there, how that affects all other planning for every other subsequent mission. But the first thing we need to look at is the requirement here. So we have 9,500 meters per second here for our delta V requirement to go from the surface of the Earth into low Earth orbit. It's a relatively conservative number. Some rocket systems can do it with less, but this is a nice round estimate that can factor in gravity loss and aerodynamic drag. So we're just gonna aim for 9,500, and that will kind of keep everything in family. So now let's start by looking at the booster, Super Heavy. So we can average its ISP out to be 340 seconds because it can start at 330 at sea level. It gets up to about 350 in space. We'll average it out to 340. Dry mass we can think is around 250 tons, give or take. Version 3 does have 3,650 tons of propellant in its tanks. And what happens is basically they need to reserve 450 tons here to be able to do its boost back burn and its landing burn. That gives us 3,200 tons of propellant to be able to accelerate. So now what we have to do is we have to take our wet mass here, which is our dry mass plus the prop that is expended plus our reserves. So basically it's our dry mass plus our prop mass. But that's for our stage wet mass. Now we're looking here at our starting mass in this column here is our starting mass of the entire stack on the stage. This includes the upper stage sitting on top of it. So our stage wet mass plus the upper stage Starship sitting on top of it. And so that's our start mass. Our end mass is, now we need to keep in mind we have our end masses from ignition on the ground up to stage separation. That burn is what we're calculating here. And so dry mass is still that same 250. We have that 450 tons of reserves. And then we still have the full mass of Starship on top of it at the very end of that burn. So that means the booster can do about 2,700 meters per second of delta V. So that's kind of our limiting factor there. So we have to always aim that our vehicle, our upper stage vehicle, Starship, has to be able to provide about 6,700, almost 6,800 meters per second in order to get into low Earth orbit. So that's actually our big number here. This is like what we're gonna be aiming at for a lot of the stuff in the rest of this video. So the way we get to this, by the way, is we can average out, like we said, the ISP of Starship to be 370 between the vacuum and the Raptor engines by throttling down the sea level Raptor engines. We have a dry mass of roughly 120 tons. We have a known prop mass of about 1,600 tons. If we leave 60 tons for reserves for the deorbit burn and the landing burn, which is actually, I think, pretty realistic. I kind of did some mass flow numbers to look at how long those burns would be. I think you can pretty safely do it on about 50 and have some margins there. Actually, I think you can do it with about 40 is the number I came up with. So I think 60 is a good number. That means we're going to expend 1,540 tons of propellant. And then we have a 100 ton payload mass. Now this is on top of your prop. So what's going to happen, so that could either be like a satellite or a space station or whatever, or Starlinks, or you can have extra propellant. And now what's gonna probably happen for tankers is it won't be like the propellant's up in the nose and it's like in its own tank. They'll just adjust the tank size to be able to hold 1,700 tons of propellant. So that's kind of how it works. At the end of the day, it's kind of the same. It's quite literally the same thing. But that's kind of the number we're looking at there. But we're considering the 100 tons as propellant when we're going to be refueling a tanker. So keep that in mind. So that means the wet mass is 1,720. The starting mass then includes the payload mass at 1,820, and the ending burn to be able to get our, by the time it gets into low Earth orbit, we're at 280 tons. So that includes our dry mass, our reserves, and our payload mass. And that gets us our 6,787 meters per second, which in total gets us over 9,500 meters per second. So again, this seems very feasible. It seems like 100 tons is something that Starship version 3 should be able to do based on the numbers. So how does this affect Starship HLS? So if we can basically replace Starship HLS, we're going to be replacing the upper stage with HLS. So HLS has to be able to get itself into orbit. So it's going to start off fully fueled. It's going to have similar numbers across the board. It's going to have 370 seconds of specific impulse. It might have more if they do 6 vacuum Raptor engines. Payload mass now is interesting because a lot of the fixed mass of the vehicle is, we kind of are going to lump that into dry mass because we have things like the cabin, we have all the chairs, the toilets, the air, there's airlocks, there's the big giant like garage, there's an elevator, there's landing legs, there's landing thrusters. There's a lot of systems that are unique to HLS. And I don't know, we're estimating that it more or less will cancel out compared to the standard Starship that has the heavy heat shield and the heat tiles and the flaps. So we'll call it a wash. Again, these numbers might be way off, that's okay. But at the end of the day, it will probably have the same 1,600 tons of propellant. And assuming they expended all the propellant, this is just kind of to get a total sense of what is the total delta V potential. It's impressive. It's 9,654 meters per second. So if this was in space, already parked in LEO and full, that's how much propellant it actually, how much delta V it would actually have. So that, technically, that's pretty close to enough to be able to properly do the entire mission if it's filled up in low Earth orbit. But let's go on because we can actually figure out why that might not quite be the case. Because remember, first, let's look at what it's going to take to refill it in the first place. So if it first gets itself, so we're now looking at this row here. So we're aiming for, it's actually over like 6,800 meters per second is what we're aiming for. We're now trying to get from the booster into low Earth orbit. So we're trying to get this number to be 6,700. And it turns out that if you burn about 1,450 tons of propellant, you'll end up with some left over, which is good because anything left over on that burn into low Earth orbit is fuel that you won't have to bring up in other tankers, right? So I estimate that you can probably get about 100, it'll probably have about 150 tons left over after that burn. It might be more, it's probably somewhere between 100 and 200 tons. That's great. But what that still means is that in order to top it all the way back off, we have to put this number back in, 1,450. So 14 or 15 launches of Starship if it's doing 100 tons per mission. This is the driving number right here, this prop expended to be able to get it into low Earth orbit. This number might be higher. It might end up almost completely empty by the time, relatively empty by the time it gets into LEO, in which case it'll need to be totally topped off. Or it might have hundreds, it might have 300 tons of propellant left over, which just means it would require less trips to be able to do the refueling portion. So that's that big driving number. Everything else is kind of the same. But now, here's the interesting thing. So if you top it all the way back off again, remember, we like doing that. We like filling it all the way back up in low Earth orbit to 1,600 tons. And if we are to get it all the way out to from low Earth orbit into NRHO and then do the NRHO insertion burn, that is roughly 3,100 meters per second to do your TLI, and then about 400 meters per second to do the insertion burn into NRHO. So we're looking to get over 3,500 meters per second. So if we burn about a little over almost 1,100 tons of prop, or 1,070 tons, we'll get that number and we'll end up in NRHO when, on its very first mission, it could be in NRHO with 530 tons of propellant left over. So technically, it would almost be enough to be able to go from NRHO down to the surface and back to NRHO on that first mission. Now, does that have the kind of margins that I would like to see and that I think SpaceX and NASA would like to see? Kind of, because you really technically only need about 5,400 meters per second to be able to really do that. And if you didn't have to worry about boil off and you didn't have to worry about, go around opportunities and rendezvous and docking and all of the other margins that you want baked in, you can do it with less. But by the time you factor in all those things, we're going to aim at 6,000. Maybe on the uncrewed one, maybe SpaceX will go for that. Maybe they'll go for, not having to refuel it once it's in NRHO. But at the end of the day, even if they just put another, filled it up from 530, it boils off, let's say 500, it's sitting there. Or maybe it boils off down to 400. You might have to get 100 or 200 tons out to NRHO. And that'll give it a very healthy margin for the rest of the trip. So that's kind of what we're looking at here. That's the big thing that we keep talking about. So it still is a lot of trips. It's still, just for the very first mission, we're still talking about 14 or 15 refueling trips. And there might be another, handful of 14, 15, 18 trips to be able to refuel it for each subsequent mission. That's a lot of refueling. Yeah, so I do think the number of refueling tankers feels quite ridiculous. I remember watching a very well thought out video from Destin from Smarter Every Day, where he was rightfully questioning the viability of using an enormous lander that requires a dozen or so rockets to get to the moon.
And I'm like, well, how many rockets do we have to do that with? And they're like, 6. And then I start, because I know people, I start calling people. I was like, dude, really, how many rockets is it? They're like, well, boil off. And okay, so I was like, some people were like, well, it's looking like 8. I was like, 8 rockets? We have to fire 8 rockets to fire 1 rocket to the moon? And then they're like, I mean, that's what they're saying, but it's probably more like 12. Really?
But there was one word in this video that changes the entire thing. He said it would take a dozen rockets to refuel it. Now the key here is that it shouldn't take a dozen rockets. In fact, if Starship ends up working out as it's planned to, this could theoretically be done with just a single rocket launching a dozen times. I mean, obviously that is extremely ambitious, that might not pan out, and the reality is, any way you cut it, we're still talking about dozens of rocket launches. Is there really nothing SpaceX can do to cut that number down? Well, the good news is there's actually a few ways that we could do this, and some of those things are easier and less painful than others. Perhaps the first and easiest thing SpaceX could do would be to simply expend a few upper stages for Starship for refueling. By expending Starship, you can basically double the amount of payload capacity of Starship by reducing the dry mass and using up any propellant margins saved for landing. So if a dozen or more rocket launches is truly scary, and for some reason that high launch cadence becomes a barrier and is the thing keeping us from getting back to the moon, they could at least have the number of launches by expending some Starship stages. Obviously, this is not ideal, but it would be a solution if launch cadence is the limiting factor. And if SpaceX and NASA was really in some kind of big time crunch and they really wanted to take this all further, they could always expend super heavy boosters and Starships, so they could get almost 3 times the payload capacity. Which in turn, of course, means they could reduce the number of launches by 3-fold at the cost of throwing away hundreds of millions of dollars of hardware per launch. Now, I really don't think SpaceX is too keen on this idea, but it is always an option. The next easiest thing we could do to reduce the number of refueling trips is to wait until Starship matures more and can take something more like 150 tons or 200 tons of propellant per launch with future Starship upgrades. When on Earth this will happen, no one knows. It will be Starship version 4 or later or whatever, but I do think it's inevitable that someday Starship will be able to carry more than 200 tons to low Earth orbit. So of course, this again could have the number of launches. And perhaps by the time, HLS is flying and flying regularly, version 4 might be the one that's flying, and this might be the case anyway. But can't we make some modifications to Starship HLS to make it simpler or smaller or something to decrease the number of refueling launches? So now I think it's time we go over some modified Starship HLS vehicles. So, it's back to spreadsheet land. Okay, so let's pull that, initial Starship HLS variant that we talked about, and we'll compare some other options to it. But starting off, I did kind of dial in to really make sure we're trying to aim at as close to 6,000 meters per second for these NRHO down to the surface and back trips. Again, that's to help kind of have some margin for boil off, margin for, all the crew rating things that we've talked about already. So that means we could actually get this done. This is the kind of the big number we're looking at here is the prop expended number. So trying to keep it this number as low as possible because that's how much propellant this vehicle is going to need in order to be able to do this trip again from NRHO down to the surface and back. So let's see if another option can reduce that number so that each subsequent trip is easier and requires less tankers. Okay, so the first option I wanted to go over was the idea of just dropping off and ditching any dry mass and just dead weight that we would no longer need after some of the high energy burns like the TLI, the translunar injection. And that actually includes roughly 26 or 27 tons of tankage that we just simply won't ever need again. There's about, almost 1,000 tons of propellant capacity that we don't really need for this trip going from NRHO down to the surface and back. So we can ditch all those tanks. Plus we have roughly 9 tons of engines, of Raptor engines that we don't technically need. We could do the rest of all this profile with just landing thrusters, right? We're in a low gravity environment. So let's see what that does. Now, we had to add a little bit of extra mass to the initial dry mass when it's taking off. We added 5 tons for all that staging hardware consideration. It's not trivial to be able to drop off hardware like the Atlas used to have those drop engines that could be ditched off like that. And it's not necessarily trivial to be able to have all those plumbing considerations and all that stuff. So we're adding 5 tons, but what that means is we're still gonna be able to ditch almost around 35 tons of hardware after that translunar injection. Okay, the next caveat though is that we're relying on those landing thrusters that have a much worse performing ISP because they're pressure fed. So their specific impulse is probably only about 320. It might be a little bit higher than that, but we'll just say 320 for now. And check out what happens then to our rocket equation here. In order to get that 6,000 meters per second, we're actually using more propellant than our standard one because of that worse performing specific impulse. So even though we dropped off a bunch of dry mass, we're still actually in a worse place off than we would be ditching all that dry mass because of the efficiency. But there's actually an even bigger problem with this, and that's because if you were to rely on pressurization and self-pressurization in a sealed container where you let boil off kind of be your header, let that be all your ullage pressure needs to come from boil off, you can't really fill the tanks up more than about half full because you have to have enough volume there and gaseous pressure to actually kind of keep the self-pressurizing loop going. So think of like a nitrous oxide tank or like a fire extinguisher or propane. You can't fill them all the way up or else you can't really get enough pressure out of them in the first place to do this, right? So that means we'd actually have to have almost half the tanks back in there anyway, or a certain amount of tankage that we can't just ditch. So now our dry mass is even higher. And so basically it's physically impossible. So just the standard stage stubby Starship ditching the Raptors and everything, not really an option. Okay, but here's another option. We could use turbo pumps. We could use turbo pumps to be able to still just suck up all the liquids out of those, smaller tanks, do the same, ditching idea, but use turbo pumps to not only increase our specific impulse, but also be able to fill those tanks up all the way with liquid. And of course, the good thing is even if you added turbo pumps and that, the mass of all that plumbing and all this, you'd want redundant turbo pumps for human factor and all that stuff. The mass actually would cancel out, or it'd probably actually be better. We'd probably have slightly lower dry mass because you don't need as much tankage. So, so the number that we're looking at here is roughly the same dry mass as kind of the stubby. We're just estimating here. But the difference is our specific impulse went up to 340 seconds, which is probably pretty realistic for an open cycle, gas generator, Methalox engine in a vacuum. The prop expended to be able to still hit our 6,000 meters per second target would only be about 510 tons. So that is actually, almost 50 tons less than our kind of de facto Starship. Okay, that's not bad, but that's quite a bit of extra complications. If we're trying to speed up a timeline, adding a staging event and adding turbo pumps now, you can't use, Raptor turbo pumps would be way too, way too overpowered for this probably. You kind of could use something like the Merlin engines, turbo pumps. Those are scaled approximately about right for the right amount of thrust if you use 2 of them for some redundancy. But now you're building new, turbo pumps running on methane and having to human rate them and all this stuff just ends up, I don't think that's going to do anything to speed up our timeline, and it really only saved us up to maybe 50 tons of propellant. So I don't think that's going to speed up anything in the long run. Okay, so next I thought, well, what if we could just ditch the tanks but keep the Raptors? And by convention you'd assume, how do you slice the middle out of a rocket? Well, a good way to do this would potentially be putting all that drop tank on top of the crew cabin and have some plumbing considerations then to be able to run the propellant lines on the outside or maybe down the middle of the cabin to be able to still feed the Raptor engines during like your translunar injection burn and other times when you're needing that extra tank volume. And then after that, you ditch off those tanks. Now you have just a lower, stubbier, shorter Starship that still has all of your your engines, your Raptor engines. It still has a decent amount of tank volume, especially if you have your Raptors. They can do heat transfer and do pressurization, autogenous pressurization inside the tanks to be able to still use those same landing thrusters. That one actually works out a little bit better. So we're assuming, again, you have more mass because of, all of the staging consideration. You actually would probably have even more mass because now you have to support all that weight above the cabin. So you'd probably have something similar to that hot staging ring, like a trellis frame or something. But we're gonna say 125 tons and roughly 90 tons. But now we get to keep that full 370 seconds of specific impulse that we so much love from those Raptor engines. And now look at this number. We only need about 425 tons of propellant to be able to get our 6,000 meters per second. And all we had to do, is still as a consideration again, is have a staging event. But that tank could be on top, it could be hiding the docking port and be an aerodynamic consideration that you no longer need once you're in space. I kind of like this one. This one's pretty decent. But perhaps the best thing about this drop tank isn't the aerodynamic consideration stuff. It's actually that by the time you get out to NRHO and you park there, you'd still have roughly 530 tons of propellant left over. So actually, you'd have enough, in theory, to do the full mission right off the bat. Right on the very first top off, once it's in low Earth orbit, you do the staging event after the translunar injection, you ditch all that dead mass, and now you have 530 tons of propellant. We're saving some for reserves. At the end of the full mission, you want to have that for attitude control and all these things. But yeah, we could actually do that on the very first mission potentially. And then subsequent missions would be a little bit less. So honestly, the drop tank isn't a bad option as far as your very first mission goes. Is pretty advantageous. And every mission after that is actually, still more advantageous. So I kind of like the drop tank idea. But that actually got me thinking, do we ever actually need all that entire tank volume? Remember when we look back at the very first initial factors that we need to get about 6,800 meters per second in order to get into low Earth orbit from the booster, that's actually our biggest burn, period. Because then after that, you already are topping it off in low Earth orbit. So if you only need to aim at 6,800 being your biggest burn, and then you have refilling events to be able to, get you back to the next stage of the mission, what if we just did a stubby Starship from the start? What if we just literally had it down to its tanks being, only as big as they need to be for the biggest burn, which is again that low Earth orbit burn. So if our tanks were roughly, about 525 tons plus, we'll say 10 for reserve, so 535 technically, that's enough to be able to get us into low Earth orbit. Barely. I mean, you're eking into low Earth orbit and you're just there almost on fumes, right? So that's not bad. Our dry mass could go substantially down because we don't have staging hardware. We can even think about how the knock-on effects of now your landing legs would need to be a little bit smaller because they don't have as much mass ever. When it's landed on the moon, you also have a smaller elevator system. All these things, if we just built it a little bit smaller, and I mean, obviously you could do things like shrinking the cabin a little bit to save a few tons here and there. But I mean, in general, this doesn't really have any compromises. We're just cutting out the tanks that are never actually necessary in between refueling. So on this, we get to keep the 370 seconds of specific impulse. Our dry mass goes down to 85 tons. And now our very first mission, we are never requiring more than 530 tons of propellant. So now, when you look at our first one, we're going to have to refill it, but we only need to refill it up to, 530 tons. We have enough to be able to do our translunar injection and our near rectilinear halo insertion burn with 135 tons left over. And then each subsequent mission, here's our magic number. It only needs a little over 400 tons to be able to top it back off, to be able to do that mission again. And now the caveat here is you'll have to do that on the very first mission, but I think we likely are going to have to do that for sure, most likely in the de facto Starship, not for sure, but most likely de facto Starship has to do that. And all the other ones that either work or don't work have to do that. But the stubby, the drop tank solution might not need to do a refueling on the very first mission, but this one for sure would. So that is kind of its downfall, I would say. But other than that, it's not very compromised. And each subsequent mission would definitely be, better. But wait, it actually gets even better. Let's dive into this one a little bit more because these numbers on the stubby Starship are actually wrong because we get to do one more thing if we actually launch with a stubby Starship. Okay, so putting the stubby Starship back onto the booster here, we're kind of going backwards again. You'll notice something, that we actually have a lot more delta V, because the stubby Starship is a lot lighter than that standard Starship. You know, it's about a third the amount of mass as the standard Starship, which means the booster actually can do more work. And wow, we actually have too much delta V, actually. So we could actually optimize this to our advantage even more, even beyond the standard stubby Starship. So check this out. If we say that we only need, for our duration of our mission, we only need 6,000 meters per second ever to be able to do that, you know, NRHO down to the surface and back to NRHO with plenty of margin. That can be our biggest burn, and we'll see if we can get the booster to do the rest of that acceleration on ascent, so that we don't have to do 6,800 meters per second on ascent with the Starship. Let's make it so the booster does more of that work. So let's offload the work. So let's get this, first we'll go kind of working backwards. We'll start by trying to get the stubby Starship to only do 6,000 meters per second. So for this, we can go down to about 370 tons of prop. That leaves 360 for reserves, or 360 that we're gonna expend, 10 ton in reserves. We can also reduce the dry mass to something like 75 tons. That might be generous, but whatever. It's, you know, just good enough to get you a sense of this. Okay, so there's our 6,000 meters per second. And look, our meters per second up here has leapt up on the boosters. The booster's able to do a ton of work. We still have almost 1,000 extra meters per second total on ascent. But we're forgetting something. We're forgetting something really important, the boost back and landing burn. We'll need to use more propellant to be able to do the boost back and landing burn, because now the booster at stage separation will have traveled further away. It's traveling faster, so it has to do more braking and it has to do more, you know, deceleration and more boost back to be able to retarget the launch site. So let's actually just increase the reserves to 825 tons. And look at that. We almost doubled our reserves. And now we have exactly 9,500 meters per second, our target delta V. The booster's doing about 3,500 meters per second of work. And then I added this column here of the boost back landing burn. So it would be able to, you know, use expend 815 tons of propellant, giving it 4,700 meters per second to be able to do the boost back and landing burn. So that should be plenty to do the deceleration and get back down. And so this is fantastic. This makes a stubby Starship look even better for the initial launch of it. And this is even just using the version 3 Starship booster. So if they went to a super heavy, you know, version 4, it could even do even more work, and this would all just continue to look even better. But I should point out that if you wanted to add any additional payload to your mission, say science instruments, excavation equipment, additional habitats, or even pushing Orion out to the moon with your Starship HLS vehicles, a stubby Starship has hard limitations. It doesn't have any spare capacity, and you can't just fill it up more like you could the other options. That's actually perhaps the full Starship HLS's biggest strength, is its flexibility for mission demands. If you need more performance or have a higher payload demand beyond the initial mission profile, cool, just fill it up more. No need to replace it and build a whole new vehicle. Just launch another tanker or two or whatever it requires to do the next mission. But of course, refilling these things for each subsequent mission could be a really big deal, since you have to get all that heavy propellant all the way out to the moon. So now I wanted to see what effect this all has on the number of tankers it's going to take to refill the Lunar depot. For this, I just used the standard rocket equation, but I solved it backwards for propellant mass. Then I applied it to 2 sequential burns, starting with what's needed to get back from NRHO to low Earth orbit. And I also included dry mass scaling with propellant volume. So the more propellant it requires, the more the dry mass goes up. We're also assuming that the depot can do some aero capture to get back into low Earth orbit from the moon. It might not do it in one shot, meaning it might dip into the atmosphere a little bit, slightly lower its orbit, then dip into the atmosphere again on the next orbit, and again and again. And it'll do that over many orbits until it's at low Earth orbit without having expended basically any propellant. This would reduce the need for a massive heat shield like the standard low Earth orbit Starship. But of course, it would need to be able to survive these little dips into the atmosphere, so you can't be too aggressive with it. So all this said, it would really only need about 400 meters per second of delta V for its trans-Earth injection at the moon to get it back to Earth. So it's a very, very small amount of propellant needed to return versus the amount required to get it out there, and while it's also pushing around hundreds of tons of propellant. Okay, so we're trying to figure out how much propellant do we need to get into the Cislunar Depot while it's in low Earth orbit from tankers so that it can get enough propellant out to the moon to be able to refill these Starship variants to be able to land on the moon. So let's start off with the standard Starship vehicle. And that, remember, it needed 555 tons to be able to go from near rectilinear halo orbit, where it will have parked after its first mission. It's going to go from near rectilinear halo orbit down to the surface and back up to NRHO. And to do that, every time it takes about 555 tons. So we can put this into this deliverable amount here. And that's going to change our total prop number over here. So let's start off with 555 tons of propellant is how much we need to get out to the moon. Hit enter, and holy crap, look at that number. 1,842 tons is how much propellant we have to get into the Cislunar Depot in order for it to deliver 555 tons to the moon. That's crazy, right? So notice again, we're expending here 1,261 tons to get out to the moon. Then it drops off that 555 tons. To get back, you only need about 16 tons of propellant to be able to get back and do a 500 meter per second return. Again, we're being pretty conservative, leaving 10 tons in reserves, but still, yeah, we require 18 and a half of those 100 ton tankers to be able to do each subsequent mission. So that's actually more than the initial mission, just to be able to do it all over again. That seems kind of crazy. So let's skip over those other stubby stage Starship ones, except for the drop tank. I want to go over to the drop tank one because that one was pretty promising. So let's do that one again. This one required 425 tons of propellant. And if we look at that one, it gets it down to less than 15 tankers. We're at 1,475 tons of propellant. But yeah, we still need, that seems wild. Still needs that much, that many tankers to be able to refill the Cislunar Depot. So yeah, that's kind of wild, right? Now let's do the stubby from the start, the optimized one that we just talked about it, where we're letting the super heavy booster actually do a little bit more work to help it get into low Earth orbit in the first place. So it's super optimized. This dry mass is only 75 tons. This thing's lean, mean, and stripped down, ready for moon missions. It only requires 360 tons of propellant. So let's put that one into this, and we're still at 1,292 tons. So almost 13 tankers to still be able to do the next missions. That's still a huge amount. But there's actually something that we have to remember is that on that first mission, we still have to get we have 90 tons of propellant in reserve when we get from low Earth orbit. So say we fill it up in low Earth orbit with its 360 tons, we still expended 270 tons to get it out to the moon on the first mission. So that means we actually have to put 270 tons back in for the very first mission to be able to complete this, because it only has 90 tons left over after its translunar injection and near rectilinear halo orbit insertion. We have 90 tons of reserve, so we need to put 270 back in it to do the first mission, to do the very first mission. So that means we're still at 1,000 tons of propellant needed for that Cislunar Depot to fill it up for the very first mission. Yeah, that's not as good as I was thinking. So here's where I was quite surprised, and obviously now you've noticed it too. Despite the stubby Starship looking really good at first and really good on paper, it has a really big problem. To do even its very first mission, it still requires almost the same number of tankers in total as even the big mega standard Starship. Like we've already just pointed out, but what's worse about this, and why it's almost worse than just using the standard Starship, is one of those refillings has to happen at the moon on the very first mission. So again, to go over these numbers, it takes about 3.5 tankers to refill it in the very first mission. Then it takes about 10 tankers that you have to refill it at the moon. So it has to do 2 dockings, right? 2 refillings with a cislunar depot and with a depot versus the standard Starship needing, 15 or 16 tankers with 1 refilling opportunity that we do in low Earth orbit. So especially for these early missions, if you're trying to simplify your mission, it's pretty hard to argue that docking twice with depots and with one of those dockings being all the way out of the moon versus just 1 depot docking in low Earth orbit is a simpler solution. Because it does look like the standard Starship could almost do this whole thing from just 1 fill up in low Earth orbit. But the most appealing option here might actually just be back to that drop tank option, because that one for sure could do the entire mission on its very first, top off when it's in low Earth orbit. So you put those 16 tankers, you fill up the depot fills this thing up, and then it can go all the way from low Earth orbit. It can for sure land on the moon and have plenty of margins, super easy. And then it's actually, each subsequent mission is a lot closer to that stubby Starship anyway. So it's kind of the best of both worlds. So this would probably actually be my pick for early missions, because it would still be, pretty sustainable, very high performance with almost no compromises, except for its big trade being in the hardware, because you now have all those staging complications and the plumbing considerations and all that stuff. That's not trivial. That's real, real considerations. But I think in the long run, that would actually be a pretty good trade in my opinion. So that's kind of the worst case scenario for these missions. It's anywhere from about 18 or more tankers down to at best probably only about 10 tankers in order to do any subsequent missions. However, this was all still targeting that near rectilinear halo orbit. So what happens if or when they move on from that? What impact does that have on these missions? So what impact does it have if we change which lunar orbit we target? Instead of targeting near rectilinear halo orbit, what if we just targeted low lunar orbit? Well, now the lander only needs roughly 4,500 meters per second of delta V for each mission, from low lunar orbit down to the surface and back. Then this is giving it a little bit of margin baked in. But if we're directly targeting low lunar orbit first, we do require more delta V to do our lunar orbital insertion burn of 900 meters per second versus the 400 meters per second that we required to get into NRHO. However, you might notice this chart shows it only takes about 4,000 meters per second in total to get from low Earth orbit into low lunar orbit versus the 4,200 meters per second that we were targeting to get into NRHO from LEO. But in total, we would save roughly 200 meters per second due to a lot of complicated orbital mechanics, including things like the O-berth effect and phasing and the little inclination changes and all the little adjustments to get into near rectilinear halo orbit. So what's it actually look like to target low lunar orbit with these vehicles? So let's do another spreadsheet for this, and this time it's going to be the best case scenarios. Now, keep in mind that we currently have no way to get Orion down to low lunar orbit, so this is definitely like a later on possibility or later on thing when either we're no longer using Orion or if Orion has a different ride capable of getting it down to low lunar orbit. So first things first, this first column for the standard Starship HLS, you're gonna notice it's the same because we're just calculating the total amount of delta V potential when we fill it all the way up with 1,600 tons of propellant. Now the next one, this changed because to get into near rectilinear halo orbit, we're only targeting about 3,500 meters per second. Now we have to target 4,000. So that burn from low Earth orbit into a TLI then also requires that orbital insertion burn. So in total, we need about 4,000 for that. That's still not really changing that much. But here's what is changing. In order to do any subsequent mission, we now only need about 4,500 meters per second to go from low lunar orbit down to the surface and back to low lunar orbit. And so even the standard Starship now only needs, only in quotes, only needs about 325 tons of Methalox to be able to get that 4,500 meters per second. Okay, I see why that's definitely easier, easier on the landers. That's why this is kind of a big deal. So now let's look at what the stage stubby with that drop tank does. So again, 4,500, this doesn't really change. The first 2 columns don't change that much. But again, when we get down to it, we drop off some of that hardware. We still, it helps. It's down to 250 tons to be able to do each subsequent mission. So again, this is looking good. And lastly, let's look at that Starship, the stubby from the start that's kind of stripped down and optimized. We're at only 210 tons of propellant delivered down to low, needing to get to low lunar orbit in order to do each subsequent mission. Okay, so that's looking pretty good, really. You can tell it actually does make a pretty big difference. It's not quite half the amount of propellant needed, but it's, I don't know, something like 40% less propellant. It's a pretty substantial and noticeable change. So now we need to do that thing though, where we plug in these numbers and have it see how much propellant we need to load up into that cislunar depot in order to refill these vehicles at the moon. Before we even start off by plugging any numbers in, you'll notice though, the vehicle's going to have to do, this depot is actually going to have to do a little bit more work. It's going to have to, get all the way into low lunar orbit. So even though landers don't have to do quite as much work because they're staying in low lunar orbit, now the depot does have to make up some of that work. It has to do a bigger burn to be able to get into low lunar orbit. And then it has to do a bigger burn to get back home and leave, do the trans-Earth injection. So leaving the moon system and then aerobraking. It has to do more work there too. So it's kind of having to pick up the slack. So let's see what this actually does. So starting off with the standard Starship, hey, we're down to less than, 1,471 tons of propellant, down from, about, 18 and a half or whatever before. Okay, so that's great. This definitely wins out there. So let's do this again for the stubby Starship with the drop tank. And we're looking at 1220. So again, I think that's a little bit better. So now let's go down to the Starship stubby from the start that's kind of stripped down and optimized for these missions. And interesting, that's actually a little bit more propellant to be able to do these missions. Now you might be going, how is that? Well, now these are my rough estimates, right? We stripped that Starship way down to be only 75 tons of dry mass. And now, in this case, we're estimating that depot to be something like 85 tons dry mass. Now again, total estimations here, this could be way off and this would then change that number. But we are having to estimate that we'd have pretty massive solar, pretty massive radiators, pretty massive, tank considerations to be able to, insulate them to prevent boil off. There's gonna be a lot of boil off mitigation. So yeah, maybe the reality is if it is a higher dry mass than the stubby from a stubby Starship, then it's actually having to do more work and it's going to cost more to be able to fill these vehicles up. At the end of the day, like I said, my numbers are not accurate enough to make that determination, but that's the real reality is like the low lunar orbit thing can help, but it's actually only really a benefit if the thing refilling it is lighter weight than the lander. If the depot is heavier than the lander, then you're actually putting more work on the vehicle that's technically less efficient. Interesting, right? Because remember, at the end of the day, the total amount of work being done is still just this, it's the same amount of work having to go from low Earth orbit to some kind of moon orbit and then landing on the moon. So the amount of work being done doesn't change between, these different mission profiles. You're just changing which vehicle has to do that work. So depending on the architecture of the lander and the depot, it might actually not make sense to target a low lunar orbit. It might almost be beneficial to target a higher orbit potentially. But for the standard Starship HLS that we're kind of using as a baseline, it could potentially reduce the propellant from, from the depot needing about 1,842 tons down to about 1,471 tons, which would of course be a pretty big win. And assuming the dry mass of the lander is higher than the depot, which I think it would be. However, there's actually one more thing we could do to reduce the number of refilling trips for each subsequent mission. And that's just only take methane on the cislunar depots. Yeah, that's it. Just don't even worry about taking oxygen out to the moon from Earth. In the future, this could be an option. Now hear me out. Okay, now this might be one of the more far-fetched futuristic things that we're going to talk about in this video, but you can actually get oxygen from the moon. And it's not even that sci-fi or unrealistic. I mean, it's physically possible and it's fairly well understood. There's actually a huge amount of oxygen on the moon, but it's trapped in the regolith and in subsurface ice. Extracting from the regolith requires a large amount of energy, but it's doable. Extracting from subsurface ice is less energy intense, but it basically requires melting the ice, purifying the water and electrolyzing it. Then you just capture the oxygen and cool it down to recondense it back to a liquid. And as ridiculous as this all sounds, there's a lot of companies working on things exactly like this, including Blue Origin, who's developed a system to turn lunar regolith into breathable oxygen and rocket propellant. But the big deal here is that oxygen makes up the vast majority of the total mass of the propellant. LOX is 78.3% of the mass of the propellant, and methane is only 21.7% of the mass for Starship. Now you might be confused as to how an engine that runs fuel-rich has way more oxidizer than it does fuel. Well, when we say fuel-rich, it doesn't actually mean more mass of fuel than mass of oxidizer flowing through the engine. It's whether or not there's more fuel or oxidizer compared to the stoichiometric ratio. The stoichiometric ratio is the exact proportions of reactants for a complete and full chemical reaction between every single molecule in your propellant. Methalox's stoichiometric ratio is 4:1, meaning you actually need, say, 4 grams of oxygen to perfectly combust 1 gram of methane. But the problem is that it's really, really hot, and you're also slowing the exhaust gas velocity down by throwing more heavy oxygen molecules. So it's actually better to add just a dash more methane, down to 3.6:1 ratio. So 3.6 grams of oxygen for 1 gram of methane, which leaves some methane unreacted. And that's a good thing, because it'll still turn into high pressure, hot, gaseous methane, and since it's the lighter molecule compared to oxygen, it'll help achieve a higher exhaust gas velocity, plus it'll help keep the temperatures lower. And now you know what we mean when we say an engine runs fuel-rich. All this said, if we don't have to take oxygen to the moon, we can greatly reduce the amount of mass needed to be delivered, which of course means less refilling tankers to fill up the cislunar depot. So in the future, this could be a big deal for frequent missions to and from the moon. So let's crunch the numbers one more time to see what this would do for our refilling depots if we only had to deliver the right amount of methane to the moon for each trip. Okay, so it's time to do the last spreadsheet of this video. At least I hope. So, and this is also the most confusing one, so hold on to your butts because this one's a little bit extra complicated. So it's complicated because you're getting the methane and the oxygen at completely separate stages. You're getting the oxygen when you're on the surface, and you're getting the methane when you're in orbit, right? So I have these labeled as low lunar orbit, and this is kind of leading into the descent phase. This is how much liquid oxygen you need left over and how much methane you need to fill it up. And then we have a separate, the next column is going from the surface to do your ascent phase. How much liquid oxygen do you need to fill this thing up in order to burn off the rest of that methane? And hopefully if we did this math right, you end up with the right amount of propellant in order to do the ascent and descent for getting into low lunar orbit. But let's go through this anyway. So for the standard Starship, where it is going to get liquid oxygen from the moon, you need to deliver 74 tons of methane in order to burn off the remaining 115 tons. So that means we're actually burning 31.9 tons of methane to burn off that 115 tons because we're at that 3.6:1 ratio. And that gets us our 23. I do have a little bit more baked in for descent than ascent because the descent phase you want more margin for your descent. You want to be able to, maneuver around. So it was intentional to try to get closer to 2,300 for descent. So now on the moon, once you're on the moon, you need to fill up 266.56 tons of liquid oxygen in order to burn off the rest of that 42.1 tons of methane. And then when you do that, you burn through 151.56 tons of methane, or of liquid oxygen. So let's do this again now with the drop tank version, and you'll see that only needs about 55 tons of methane delivered to the moon, to low lunar orbit. And again, the best in this case is the fully stubby Starship, which needs about 46 tons. Okay, so you can probably see where this is going. So now let's see what impact this has on the cislunar depot. How much propellant do we need to get into that cislunar depot in order to deliver X amount of methane to the moon, and only methane. So that's kind of the key here. So let's start off with that standard Starship. We're at 74 tons. So it's going to take only 630 tons of propellant. Hey, that's not bad. If that's version 3, we're down to like only 6 launches. If that's version 4 or later, it might only be 4 launches. So let's see, what about the drop tank down to 55 tons? We're down to 566 tons. Again, an improvement, we'll take it. And lastly, 46 tons, 536. So there's not even 100 tons, is that right? There's not even 100 tons difference. There's right about 100 ton difference between those two. So if they're doing, liquid oxygen production on the moon, all of a sudden the Starship, the full standard Starship, actually kind of has that advantage of it's not as big of a deal. It's like you can have all that potential now too. If, say, we're trying to unload, 100 tons of actual payload along with this, which would add to this calculation, make it even more complicated, then the standard Starship has those margins, and you actually could start to go, hey, look, we could actually, load this thing up more, fill up more oxygen from the moon. Yeah. But it's pretty crazy. So we can get down to, at best, we're still a little over 500 tons. But even the standard Starship, in this case, is a little over 600 tons. So that's not bad. Okay, so that's definitely our absolute best case, far future example using the kind of built-in Starship architecture that we're familiar with. And if we are producing liquid oxygen on the moon, it would greatly reduce the total number of tankers needed to fill up the cis lunar depot in order to pull off each and every subsequent mission. But looking back, our worst case scenario was up to 1,842 tons of propellant needed for that cis lunar depot to do the job. And we could probably get that down to about 630 tons for the standard Starship. Regardless of the number of Starship launches, it brings up one last huge issue. If we're potentially needing to launch, 5 or 10 or 12 or maybe even over 18 fully fueled, full stack Starship rockets, do we even have the propellant capacity to keep up with all that demand here on Earth? With Starship requiring almost 6,000 tons of propellant per launch, you need an absurd amount of trucks delivering all that propellant to the launch site. And it's not just what fits in the vehicle, there's even more you need to operate a launch site. In total, we're talking about something like 250 trucks for liquid oxygen, nearly 100 trucks of liquid methane, and over 150 trucks of liquid nitrogen per launch. So that's over 500 trucks per launch of Starship, and that's only for version 3. SpaceX is already consuming a very large portion of the available liquid oxygen in the southern half of the United States, and that's just for the Falcon 9. Once Starship starts flying regularly, won't they quickly hit a bottleneck in just being able to get their hands on commodities? The answer is yes. Right now, with the systems in play at the moment, 100% yes. Just getting their hands on all the propellant for each and every launch will be a challenge, and it could even provide some minor delays between launches if things get dire. The solution is, well, we're actually already seeing part of the solution. SpaceX is building their own air separator units, or ASUs, right there at the launch pad at Starbase. Air separators are the giant plants that take in air, they condense it down into a liquid, and then they distill it out from nitrogen and the oxygen and other trace elements. Once the ASU is running, this will greatly offset the oxygen supply trucks, perhaps completely by producing the oxygen right there on site. And beyond that, there's already companies building new air separator units near the launch sites at Brownsville, near McGregor, and out at the Cape. There's even an environmental document that mentions building an on-site propellant generation capability that would include both liquid oxygen, but also the liquid methane right there at the Cape. Not to mention, there's always been talks about trying to bring methane in directly on a pipeline, which would completely eliminate all the needs for those trucks too. So despite this being a massive demand on a scale that no one's ever even remotely seen before, they're at least working on it, and by the time HLS is flying, hopefully they have some of these on-site productions online to help them keep up with the thirsty demand of this beast. Okay, I think that covers pretty much everything as far as just the practicality and the logistics of something like this. So I think it's finally time we summarize this whole thing. So to summarize, Starship is ridiculously tall. And in order to not tip over on the moon, SpaceX is going to have to rely on self-leveling landing legs, and they could also lower the height with some shorter vehicle options that I personally would love to see played out. SpaceX is continuing to use Methalox as their propellant of choice despite it not being hypergolic and despite it being cryogenic and prone to boiling off. They can and they will need to address these issues, neither of which are physically impossible. And the dozens of refilling tankers? Yep, that's gonna have to work with this current plan. Are there ways to reduce that number? Yes, by expending hardware and shrinking the vehicle. Will SpaceX do that? If things work out how they want to? No. Eventually, there could even be ways to reduce the number of launches by harvesting oxygen from the moon, and also by targeting low lunar orbit and skipping over NRHO completely, which could help reduce the number of full stack launches here on Earth, which is maybe a long ways into the future, but it would hopefully get better instead of getting worse. Is Starship HLS even feasible? Technically, yes. Is it the easiest solution for a lunar lander? Absolutely not. However, by keeping it based on the full Starship design, they are greatly reducing the engineering workload, and in some ways, they're actually kind of simplifying it. They're trading engineering a new vehicle with bespoke engines and propellant and unique structures for refilling tankers and more launches. To SpaceX, I think if the solution is either engineer an entire new system or just fly a few more tankers, they'll choose to fly a few more tankers every single time. And as I'm sitting here right now, this all sounds impossible. It sounds like the much harder option. And personally, having watched many Starship prototypes blow up with my own eyeballs, it feels like a terrible idea. But let's flip this around. What happens when they do get Starship to orbit? When they do land both the booster and the ship? When they do reuse them? And when they do dock two of them together and transfer propellant? And then when they do that again and again? Basically, once and if they can prove orbital refueling even a single time, it's basically game over. Anything beyond that, it becomes more and more arbitrary. Suddenly, it goes from a terrible idea to kind of the obvious choice. Why would you do it any other way if you have the option to just refuel in orbit and launch absolutely absurdly massive and capable vehicles on the moon? And why waste the resources to build a system that you'd be eager to replace, that could basically immediately after the first or second launch become completely obsolete? I think Lori Glaze, who's NASA's acting associate administrator for the Exploration Systems Development Mission Directorate, that's a mouthful, I think she said it best at NASA's recent Ignition event.
We've also heard that simplifying the mission requirements for this initial mission while maintaining their long-term capability is also a strong desire. We want to simplify, but we also want to make sure we're building towards the future. So it's important to assure that whatever architecture we're using for Artemis 4 feeds forward to what's going to be needed in the future.
Now, this all being said, I do wish that NASA, and more specifically SpaceX, had aimed at just simply a smaller size and target in the very first place to ensure that humans get to the moon sooner rather than later. But then again, within a few landings, everyone would just be anxious to move on to a sustainable and larger architecture. And all that time, money, and development would be for naught. Imagine if we just rebuilt the Apollo lunar lander. Everyone would be yelling, wait, it's been over 50 years later, and this is still the best we can do? We need to be aiming at big. Now, of course, my last sentence here is gonna be like a total mic drop. I still wonder how they're even going to talk NASA into certifying this whole thing to be human rated. But let's just not even go there for this video. We already went through enough. That's a whole nother topic. Maybe I'll do a video on that someday on how I personally wish it had like an emergency abort capsule on top or something, because yeah, it all still makes me just really nervous. That's what SpaceX is aiming for. But will this really be a thing by 2028? I mean, who knows? Probably not. Because in my opinion, Starship landing on the moon by 2030 is still quite ambitious. But what do you think? Do you think Starship HLS is just simply too ridiculous? Do you think it will ever land on the moon? Do you think it's a good thing they're going all in on size so they don't have to keep re-engineering new landers over and over to build a full-scale system capable of building out a moon base? Let me know your thoughts or questions in the comments below. I owe a huge thank you to our Patreon supporters, especially our mission directors here. If you want your name on screen or if you want to support the work we do, head on over to patreon.com/everydayastronaut or become a YouTube member or an ex-subscriber, or you can even find us now on Nebula. By the way, if you use go.nebula.tv/everydayastronaut, you can get 50% off. I'm a big Nebula fan, so sign up if you want to check it out. And once again, don't forget to go to everydayastronaut.com/shop and check out our new Translunar Coast collection that features our sun-kissed isocyanate shirt, our slow roll towing shirt, our Translunar Coast shirt, Artemis X-Core hats, discounted shirts at just $10, our model Falcon 9 rockets, and so much more at everydayastronaut.com/shop. Thanks everybody, that's gonna do it for me. I'm Tim Dodd, the Everyday Astronaut, bringing space down to Earth for everyday people.